Okay, so the topic of today's video is we're going to start talking about differential analysis. So if you recall, for the last couple of weeks, we've been talking about integral analysis, which develops equations for control volumes. So differential analysis is different from that in the sense that integral analysis allows us to solve for gross or system level behavior, but it doesn't give us point by point details to what the fluid flow is doing. So that's why we want to take a look at differential analysis now. So just to kind of illustrate this point, if we were to, for example, take a look at a wind turbine, integral analysis would, if I take a look at a wind turbine here, like so, integral analysis would allow us to know what kind of torque do we need to generate to spin these blades, or what kind of fluid flow is going to generate a desired torque output, that kind of thing. But it's not going to give us point by point details, such as what does the pressure look like along these blades of our turbine? When would we expect it to fatigue or fail or bend? So there's a lot of problems in which we would really like to know the real details about what's happening in this system. Okay, so to do this, we need the differential forms of the conservation equations that we've been talking about for a long time. And to do this, we're going to kind of use the same approach as we had been using before, where we start with a little volume, like so. So here's my little infinitesimal cube, and I'm going to have a point at the very center of it that I call O. And I'm going to have my coordinate axis here, so X, Y, and Z. And here we have our velocity, just as the same as always, consisting of a little u to denote the I hat or X aligned direction, a little v to denote the j hat or y aligned direction, and then a little w to denote the k hat or z aligned direction. Okay, so we need quantities at each of the faces on this cube. So to find that, since we know our velocity at our point O, which is in the center of our cube, we're going to do a Taylor series expansion to find the values at the faces. And I should note here that the lengths of our cube are dy, dx, and dz, as you might have expected for an infinitesimal volume. Okay, so if we take a look at the density first, the density at a point of x plus dx over 2, so we're looking at this rightmost face here, is going to be equal to the density at the center point plus the derivative with respect to x dx over 2 plus the second derivative of the density with respect to x plus 1 over 2 factorial, and then dx over 2 squared, plus many more higher order terms. Okay, so this is a Taylor series expansion to find the value of the density at dx over 2 distance away on the right-hand face. So these are higher order terms. We're going to neglect them. Okay. And the reason for this is, as we've done in class before, here you'll notice there's a differential, it's squared. We normally get rid of anything that has differentials times other differentials, because we know that the differential amount is supposed to be infinitesimally small. So if we square that value, it's going to be even smaller. So there's no point keeping that around. Okay, so here we want to take a look at all 6 of the faces that appear on this cube. On the left-hand face, kind of in a similar fashion, we want to look at the density at x minus dx over 2. And that's going to be equal to density plus d rho dx times negative dx over 2. So here we've got our density minus the differential of rho with respect to x times dx over 2. Okay, and so at this point, we should recall that our conservation of mass in integral form looked like the following. We have our time derivative of the integral over the control volume of the density integrated over the velocity or the volume, plus we have our integral over the control surface of the density, the velocity dotted with the area, integrated over the control surface, and then this is of course equal to 0. Okay, so we want to take a look at what is this quantity, so this control surface integral. We want to take a look at what this is in the differential form. So we're going to take a look at this rho v dot dA over each 6 of these faces in this form here. And what this term is called the momentum, or sorry, the mass flux. So we're going to be looking at the mass flux for an infinitesimal value. We're looking at the control surface integral for the mass flux at the surfaces, which is the density and then the velocity vector dotted with the differential area. And if you remember, for an assumption of uniform flow when we did integral analysis, we could say that this was the summation over all the control surfaces of rho v dot A. Right, so we're going to leverage that now and assume that since we're looking at a teeny tiny little cube, we can approximate the velocity as being uniform at these surfaces. And the reason we can do that is if we have, some really interesting velocity profile. If we zoom in close enough to say here, if we zoom in here, this velocity profile is essentially uniform if we have our little slice of it be small enough, which is the idea. Okay, so we want to take a look at the sum of the velocity dotted with the area over each 6 of these faces on our infinitesimal little cube. All right, and so we're going to leverage our Taylor series expansion of each of our terms at these faces. And I'm going to write down what this looks like for all 6 of the faces. Okay, so starting with the left face. So this would be the negative x direction. Here we have negative rho minus d rho dx, dx over 2. And then we have our velocity, u minus du dx, dx over 2. And let's not forget our area, which is dy dz. Okay, so let's just talk about this one for 1 second before I go on and do the other 5. So here we're taking a look at this face right here. All right, and so we're assuming that our velocity is oriented in the positive direction. So it's flowing in the positive x direction. And as you'll remember from the last unit, the unit area normal is always pointing out from the surface face, right? So the left side in the negative x direction of our cube is going to be pointing in the negative x direction like this. So this is going to be our A vector, right? And so in that case, that's why we have this negative here. And we have, this is our expansion of our density to get us from that center point of our cube to the left surface. And then the same thing for our velocity. And then of course we need our area of that surface. So since this is in the x direction, we have dy dz are the two sides of our faces. Okay, so let's take a look at the right side of our cube, which is the positive x direction. And that's going to look like positive. So, right, we have our velocity and our area pointed in the same direction. So we have a positive rho plus the differential of rho with respect to x dx over 2. And then the same thing for the velocity. And again, our area is dy dz. Okay, so we're just going to move along the cube and do the top and bottom and then front and back sides. So next we'll do the bottom, which is the negative y direction face. This contribution is given again as a negative. So we're assuming that our velocity is oriented in the positive direction for each direction of the flow. So our velocity is pointed up here. And then on the bottom face, the unit normal would be pointed down. So we have a negative rho minus d rho dy this time, dy over 2. And then v, so the y component of velocity, minus dv dy, dy over 2. And then of course here the area of our face is dx dz. All right, and then similarly for the top surface, so this is the positive y direction, we're going to have now our velocity and our unit normal oriented in the same direction. So we have a positive rho plus d rho dy times dy over 2 v plus partial partial v over y dy over 2. And again, our area is dx dz. Okay, so this just leaves our last two surfaces. So first, we're going to go with the back face. So this is the negative z direction. Again, just like in the x and the y direction, here we're going to have a negative because the velocity and the unit normal for the area vector are oriented in opposite directions. So we have rho minus d rho dz dz over 2 times w, our z component of velocity, minus dw dz, and then dz over 2. And then here our unit area is dx dy. Okay, and then so our last surface is the front surface. So this is the positive z direction. And that is positive because our velocity vector and our area vector are oriented in the same direction. So we have rho plus d rho dz, dz over 2, and then w plus partial w partial z, dz over 2, and again, dx dy. Okay, so when I put all of these together, you will notice, maybe just scanning these vertically, you'll notice that the left and right, bottom and top, back and front faces, there's some cancellation that occurs here. So you'll notice that this density and this density, this density, this density, this density, this density, they all cancel out, especially with the leading term. So rho W, negative rho W, rho V, negative rho V. So these terms are all going to cancel out, and we get a nice, much simpler equation when we combine these terms. So we're adding them all together because, remember, we're assuming uniform flow at all of these surfaces, and we're adding them all up, just like how we did in the integral analysis. Okay, so when we add this all together, what we end up with is we have a partial rho u. Now, let me back up. Okay, so when we add all of those terms together, what we get is we have in the x direction a u partial rho partial x plus rho partial u partial x. In the y direction, we have a v partial rho partial y plus rho partial v partial y. And then in the z direction, we have a w partial rho partial z plus rho partial w partial z. All right, and if you look at this for a second, you might notice something convenient going on here. So this is actually, we can kind of collapse this a bit more. We can write this as this first term is just the same thing as if we took the derivative of rho u dx, and we just do the chain rule or the product rule and expand it out, and it's the same thing. And likewise, in the y direction, we have the partial derivative of rho v with respect to y, and then the same thing in the z direction, rho w with respect to z. And let's not forget our area, dx, dy, dz. Okay, so if we combine this together with, if you remember, there's an unstudied term to the conservation of momentum. That term is d rho dt is equal. Okay, so one last thing to note here is that you might remember that the gradient operator looks like this. So it's denoted with this del operator, and it's given by I hat d dx. So this is the derivative in the x direction, plus j hat, partial derivative with respect to the y direction, plus k hat, partial derivative with respect to the z direction. Okay, and so if we look at this term a little more closely, we notice that this is the same thing as writing it as the gradient operator, which I've written right here, dotted with a rho times the velocity vector. Okay, and so when we combine this with the unstudied term in the conservation of mass, so remember, we also care about our change of mass in our control volume with respect to time, then we end up with d rho dt plus the control surface flux of the mass out, which we're saying is the gradient dotted with rho times the velocity vector is equal to 0. Okay, and this is what is known as the continuity equation. Which is just another way to say conservation of mass. This is an important result. And so I'm putting it in a box. Okay, just to talk about this mass flux term here for 1 second more. We will note that in the case of an incompressible flow or the case of a steady flow, some interesting and helpful simplifications happen. Okay, so if we have an incompressible flow, we've talked about this before, right? This means that our density is a constant. All right, so if we take a look at this equation, then we know that, of course, our density is not changing with time, so this goes away. And then also our density doesn't vary in space. So we're going to take this out of the gradient operator and cancel it out with the 0. So in this case, our continuity equation just becomes the gradient operator dotted with the velocity vector is equal to 0. Okay, there's a few things to note about this. This gradient dotted operator is the divergence operator. So this will sometimes be called divergence-free flow. And a good way to think about this is the sign on this term kind of gives you a sense of if mass is flowing in or out of a point in the flow. So here, the divergence is 0, right? In the case that it was less than 0, if it's less than 0, if we take a look at this equation here, then that would mean that our density as a function of time is increasing, right? So this is less than 0, so it's negative. So when it moves to the right-hand side, it's positive, meaning the density is increasing with time. So a little picture that I like to use to remind myself of this is if we think of a point in the fluid, our density is increasing with time. And this means that flow matter is just coming into this point. So it's like matter is being created and it's increasing in density over time. In the event that the gradient or the divergence of velocity is greater than 0, the opposite is true. It's becoming less dense over time. So if this is positive and we move it to the right-hand side, it becomes negative, which means our density is decreasing over time. So if we look at our same little point in the flow, then we can imagine that matter is just kind of scattering from that point. Okay, and so this is a good way, at least that I find, to think about the divergence operator and kind of what it means physically. This can also, the divergence of V can also be called dilatation. So you can kind of think of like the dilation of an eyeball when your iris contracts or dilates, for example. Same kind of idea here. We have matter coming in or going out. It's kind of contracting or expanding. Okay, in addition, we can also have a condition of steady flow. So if flow is steady, we know that all of our derivatives with respect to time are going to go to 0, right? So that means kind of similar to this equation, our continuity equation now becomes that the divergence we have the divergence of rho times the velocity is equal to 0. So you'll notice here now, instead of just the velocity in this operator, we have our density hanging around as well. And that's just because we've said nothing about compressibility at this point. We've only said that it's steady. Okay, so we got to keep the density. All right. So now we need to turn our attention to the momentum equation. If you remember from integral analysis, our two big tools that we had were conservation of mass and conservation of momentum. So this is our differential form of conservation of mass. And now we want to figure out what is that same differential form, but for conservation of momentum.